Discrete Fourier transform. In this chapter, we'll discuss about computations in DFT.
Parseval's energy theorem. According to Parseval's energy theorem, energy in time domain is equal to energy in frequency domain. Energy in time domain is defined as summation of mod value of x of n square, where n varies from 0 to n minus 1. This energy is always a real term and always a positive term. Energy in frequency domain is defined as 1 upon n summation of x of k square, where k varies from 0 to n minus 1. Energy calculated in time domain is exactly same as energy calculated in frequency domain. So to verify this, let's take one example. X of n equal to 1, 2, 3, 2. First we'll calculate energy in time domain by basic definition of this energy. Here it is a sum of every sample value square. 1 square plus 2 square plus 3 square plus 2 square. And this value is equal to 18. So energy of this signal is 18. Let's calculate this energy in frequency domain. For that, first we have to calculate. We need to calculate x of k. Let's say that this x of k is already calculated, and x of k equal to 8 minus 2, 0 minus 2. Now by basic definition of calculation of energy, 1 by n summation of x of k square. That means 1 by 4, there are 4 values. 8 square plus minus 2 square plus 0 square plus minus 2 square. Each value, mod value of square of the magnitude. So this is 18. This is exactly same as that we obtained by time domain method. That means energy in time domain is exactly same as energy in frequency domain. Magnitude spectrum and phase spectrum.
Spectral analysis. So we'll take multiple cases here. The first case is find DFT of 4-point sequence x of n equal to 1, 2, 3, 4. By definition of DFT, we'll get x of k equal to 10 minus 2 plus 2j minus 2 minus 2 minus 2j. The magnitude will be 10, 2.82, minus 2 will change to 2, and this will be 2.83. X of k is defined for k equal to 0, k equal to 1, k equal to 2, and k equal to 3. And the corresponding value of omega is omega equal to 0, omega equal to pi by 2, omega equal to pi, and omega equal to 3 pi by 2. When we use DFT, the magnitude spectrum is only on positive side starting from k equal to 0, that is omega equal to 0. So at omega equal to 0 it is 10, magnitude value is 10, omega equal to pi by 2, this magnitude value is 2.83, omega equal to pi, this value is 2, and so 2 here, omega equal to 3 pi by 2, this is 2.83. And if you continue this for the next value of x of k equal to 4, you will get first value repeated, so this value is written here, but this is not part of DFT. Because x of omega is continuous function of omega, when we convert this signal from time domain to frequency domain, and when we obtain this magnitude spectrum, we get continuous function of omega. The spectrum is continuous function. So all these points are joined by simple freehand drawing. First point to second point, second to third point, third to fourth point, and repeated. This is magnitude spectrum after finding DFT in the range of 0 to 2 pi. Case 2. To find DFT of 0 padded signal. Here x of n is 1, 2, 3, 4 followed by 4 zeros. When we append the signal by 0, the signal doesn't change. That means the x of n is same as what we had taken earlier, that is 1, 2, 3, 4. When signal is not changed, then spectrum should not change. Let's see what we get. So we have to find x of k by taking n equal to 8. We'll get 8 values of x of k, and then we'll find magnitude spectrum. We'll get this magnitude value. These values are defined for omega equal to omega k by 2 pi k by n. Here n is 8. So the frequency difference between these two values will be pi by 4. First value is 0, omega is 0, so that is 10. Second, at omega equal to pi by 4, it is 7.25. Next, 2 pi by 4, then 3 pi by 4, and so on. So this time we are getting 8 values, but the spectrum is defined in the range of 0 to 2 pi. That means for the same signal, now we are getting 8 values. That means we are getting more number of points on the spectrum. And as number of points are increased, we are getting better approximation of the original spectrum. As compared to n equal to 4, here we are getting more resolution, more number of points, and therefore the quality of the spectrum is improved. This is case 1 for the same range. Now we are getting another spectrum, but this is actually same spectrum with better resolution. Now we are getting for 8 values. This is spectrum with only 4 values. This is the spectrum of the same signal using 8 values. So here we are getting better approximation of the original spectrum. Signal is not changed by 0 padding in the time domain. Therefore, spectrum in frequency domain is also not changed. What we are getting is a better or accurate spectrum, more accurate spectrum. Here we are taking x of n with alternate zeros. When signal is inserted alternate zero, that means actually we are expanding the signal. Signal is expanded in time domain, and the effect of that expansion we can see here. The spectrum is compressed in frequency domain. As compared to the original spectrum, which was same as this but in the range of 0 to 2 pi, now it is compressed to the same shape in the range of 0 to pi. So let's do this close analysis. This is in the range of 0 to 2 pi. The same spectrum is obtained here, same values in the range of 0 to pi. That means signal is expanded in time domain, but spectrum is compressed in frequency domain. So expansion in time domain corresponds to compression in frequency domain and other way around. Compression in time domain corresponds to expansion in frequency domain. Signal is expanded by factor 3, so spectrum is compressed by factor 3. First compression, second part, third part. DFT converts sequence from time domain to frequency domain. DFT converts n samples from time domain to n coefficients in frequency domain. Every value of signal is called sample. Every value in frequency domain is called coefficient value. Frequency domain coefficients are separated by omega equal to 2 pi by n. The frequency difference between two coefficients is 2 pi by n. When the length of signal x of n increases, the frequency spacing decreases. The frequency between two coefficient value decreases, and therefore error in the representation of the spectrum also increases because we get better resolution, better version of the original spectrum. Resolution of the spectrum increases. Resolution means number of points per unit length, and so the accuracy in the representation of the spectrum increases. When the signal is expanded in time domain, the spectrum is compressed in frequency domain. That means expansion in the time domain corresponds to the compression in frequency domain by the same factor.
Coursera is an online learning platform designed to provide high quality structured education in a flexible and accessible way. The platform offers academics and professional courses across science, technology, engineering, and in management. Visit www.coursera.in. Midnight Masterclass is a YouTube channel, and we welcome you to Midnight Masterclass, your late night destination for learning that is actually fun.
Thank you.